Section 12.2, Variation. In the previous section, we were looking at proportion problems. And with variation, we're going to be able to handle the same type of problems, but we're also going to be able to add some structure to that and a little bit more power where we can handle additional situations as well. So it'll feel a little similar in terms of the wording of the problems. We'll attack them in a different way, but in a way that allows us to do bigger and more things. So let's go ahead and start off with the definition, direct variation. If y equals k times x for some non-zero constant k, then we say that y varies directly as x, or that y is proportional to x. So right away you see that idea that varying directly is related to being proportional, but the key thing is this translation. If they say that one variable varies directly as another, then that means that the first variable is equal to a constant k times the second one. So when we read this, we're going to translate to that. And we call that k in that equation the variation constant, or the constant of proportionality, and the equation y equals k times x is called a direct variation equation. So then what does it mean for things to vary directly? So this next box tries to get at that idea. So what are the changes in the values of the variable for direct variation? Assume that y varies directly as x with some positive variation constant k. Then if the value of x increases, then the value of y also increases, and if the value of x decreases, then the value of y will decrease. So what they're telling us here is those variables move in the same direction. If this finger represents x and this represents y, they're saying if x goes up, y goes up. If x goes down, y goes down. So with direct variation, the variables move in the same way. One goes up, so does the other. One goes down, so does the other. We'll be looking at something called indirect variation later, which deals with the opposite sort of situation. All right, so let's go ahead and jump in and look at an example to see how direct variation works. Find an equation that meets the given conditions. C varies directly as u, and C equals 12 when u equals 3. All right, so the first thing in finding that equation is, here's an equation, right? So we want to take the wording like this and write it into an equation like that. So when they say C varies directly as u, that means the first variable is equal to k times the second one. So I can take that and just translate that directly into C varies directly as means equals k times, and times what? The second variable, which would be u. So this would be the answer to find the equation, except for that to really feel like we found the equation, we need to figure out the constant of proportionality, or the variation constant k. And the way you do that is you plug in these other values that they're giving us. So when they say that C equals 12 and U equals 3, that's going to help us figure out what K is. So C equals 12, so we'll plug a 12 in for that C. When U equals 3, so for that U, we'll put that value of 3. Whoops. Let me write that one more time. So the 12 equals K times the U, which is 3. And then we just want to solve for K. And that 3 and k are connected by multiplication. So if we divide both sides by 3, that would cancel. So we divide the other side by 3 for balance. And then we get our value of k when we reduce. K is equal to 12 over 3, which is 4. But this isn't our equation. This is the equation. It's just that we need to plug that value of k in. So a lot of people, they figure out what the k is and they feel like, oh, I'm done. You're almost done. You just need to take that with the original equation and put them together and say, okay, my variation equation is C equals K, which we now know is 4 times U. And there is the equation of variation. And that may not feel very similar to what we did in the previous section because we have such a different approach. But you'll see as we get to the applications, we solve similar types of problems with this approach as what we did in the previous section. You might also think like this is a little more complicated, and it is, but it's also more powerful, allows us to do bigger and better things, and eventually can be even faster than what we were doing in the other section. Let's look at another example. If p varies directly as t, and p equals 18 when t equals 3, find p when t equals 5. So this is actually the type of problem that you could do with proportions, where you would think about the ratio of p to t here and p to t there and solve. But we're going to set it up as one of these direct variation equations because we need to learn how to set these up so we can do the more powerful things and get some extra repetition and answer multiple questions by taking advantage of the equation. All right, so let's do the same sort of work we did here. They say p varies directly as t, so that means that p is equal to some constant times t. So that's the initial setup. So there's the first form of our equation. Now we want to figure out what the k is. We're going to do that by plugging in these values of p and t and solving for k. So if I do that, for p I would put the 18, the k stays, and the t is 3. So we plug those in, and then we just want to get k by itself. So divide both sides by 3, and we get k equals 6. And now, just like last time, we'll take the k equals 6 and we'll plug it into that initial equation. And then we will have p equals 6 times t. So there's my variation equation. Only this time, that's not the answer to the problem because they have an additional question. They want us to find p when t equals 5, but that's what this equation is good at doing. So they're telling us to find p when t equals 5. So we're going to plug that 5 in for t right there. So p will be equal to 6 times 5, which is equal to 30. So p equals 30 is the answer to the question, and we use the equation to get that. And again, we could have used proportions to solve that also. The proportions might even seem like a simpler way to do it, but in the long run, we'll have an advantage to having this equation. The two main advantages are, if they asked us several questions like this, what about when t equals 9? What about when t equals 8? What about if t equals 2/3? We could just keep plugging those in and getting quick answers because of the work we did here. And then the other advantage is there's some problems we can do with variation, especially when we start looking at indirect variation that the proportions couldn't handle. And we'll see that as we continue to move through this section. If y varies directly as w squared and y equals 6 when w equals 3, then find w when y equals 54. So if we take this first part, where it says if y varies directly as w squared, we know that if it says varies directly as, we're going to substitute k times there. So we're going to say y equals k times, and then it says w squared, so we'll put that in there. So that's kind of the format of our equation, and now we want to use these constants right here or these givens to figure out our constant. So they say y equals 6 when w equals 3. So we're going to take that and plug in the y equals 6 right there, and then the k we don't know yet, and then times w squared, which would be 3 squared. So we have 6 equals k times 9 if we do the square on the 3. We divide both sides by 9. That would cancel the 9's off. And we get k equals, and we can do some reducing there. 6 and 9 are both divisible by 3. 3 goes into 6 twice and into 9 3 times. So we can say that k is 2/3. And once you figure out your constant, now you can write that into your equation and say, okay, the equation of variation is y equals 2/3 times w squared. And then at that point we can use this equation to finish off the problem and find w when y equals 54. So we're going to go ahead and plug the 54 in for y. And this is a little bit unusual. On most variation problems they give you the input over here, but this time the y equals 54 is the left side. So I'll plug that in. So 54 equals 2/3 times w squared. And it's been a while since we've done this, but if we have an equation where to get the variable by itself you just need to get rid of a fraction multiplier, then you can multiply both sides by the reciprocal of that fraction. And the 2's would cancel and the 3's would cancel, and we'd have w squared by itself. And then over this side we could make that 54 over 1, and 2 goes into 54 27 times, and 3 times 27 is 81. So that would get us to 81 equals w squared. And then to solve for w, we could take the square root of both sides or raise both sides to the 1/2 and say that w is the square root of 81. But one of the things that we might remember from previous chapters is that if you're taking an even root, then you're supposed to give both a plus and a negative answer. So w could be either positive, W could be equal to either positive or negative 9. And remember, when you do this sort of work on My Math Lab, you would enter the answer as positive 9 comma negative 9. But they are going to expect both the positive and the negative answer there from you. Okay, so let's go ahead and look at a template for kind of the steps we would do when we're working on a variation problem. So these are the steps for finding and using a direct variation model. Assume that the quantity P varies directly as the quantity T, and we want to make estimates about an authentic situation. Then substitute the values of the point into the equation P equals K times T, and then solve for K. I think we could list a step 0 there, which is to write the equation that P equals K times T, because whenever they say we have direct variation, you would do K times that variable. And then what they're saying is if you're given some values like we were the 6 and the 3, then you want to plug those in to figure out what the K is. Once you've figured out what K is, substitute that into your equation. So once we found the K was 2/3, we plug that into the equation to get this format. And then once you have that equation, they're saying in step 3 here, you can start using that to make predictions. And we did that when they told us that Y was 54. We plugged that in and we solved for the W. And then again in this one, we had to be careful to remember to give both the positive and the negative value when we took an even root. Let's go ahead and look at another example. The distance d in miles that a student travels by car varies directly as the travel time in hours, t, and the student travels 93 miles in 1.5 hours. Find the equation that describes the relationship between time and distance. So the first thing is the distance d that a student travels by car varies directly as the travel time t, so that means that d is equal to k times t. So I'm going to write that down first, d equals k times t. That would be like the step 0 that I talked about up here. And then moving on to the steps that the book gave us, substitute the values of a data point into that equation and solve for k. Well, the data point they gave us is 93 miles and 1.5 hours. So the 1.5 hours, that is a time, and the 93 miles, that is a distance. So we'll plug the 93 right here, and the time of 1.5 right here, and then we would try and solve for k. So I could divide both sides by 1.5, and those would cancel off. And then let's go ahead and see what we get for k when we do that. Whenever we have a decimal, I think it's reasonable to go ahead and divide and give another decimal. So 93 divided by 1.5 actually turns out to be a rather nice number. We get k equals 62. And then they said to find the equation. This is not the equation. This is the equation. But to really consider that you found the equation, you have to have figured out the k and plug that in. So we take that equation we had already, and we take what we just learned that k was 62, and we plug that in, and we get d is equal to 62 times t, and that is the equation of variation that they're looking for that describes the relationship between the time and the distance. Okay, moving on to the next page, we're still just continuing on with that previous example. We have our equation set up, and now they're starting to ask us some questions about it. How far would the student travel in 2 hours? So when they give us the 2 hours, they're telling us that t equals 2. We have our equation from the previous page right there, so we substitute into that and get d equals 62 times 2, and we do that multiplication and we get 124. Then we should think about what are the units on that. Well, that is the distance d, and back in the original statement of the problem we learned that d was given in miles, so that would tell us that the student would travel 124 miles during that 2-hour time. And then very similar, they ask us another question, how far would they travel in 3.6 hours? So we just substitute that in now, and we get d equals 62 times 3.6. This one's a little bit messier, so I'll go to the calculator for that. 62 times 3.6, we get 223.2. That's still a distance, so that would still be a number of miles, so I'll put the units on there. And that finishes that off. This shows one of the advantages of having a variation equation rather than just doing work with proportions. If you're being asked more than one question to make more than one estimate, then it's nice to have the equation all set up so you can just quickly substitute into there and get answers without having to do the algebra again and again each time. And then finally they ask, what does the constant in the equation represent? So they're asking about that 62. So let me just take the equation d equals 62t and point out what I get if I solve that for 62. I could get rid of this t, which is connected by multiplication, by dividing both sides by t, and those t's would cancel. And so that 62 represents distance over time, and distance is in miles. So on the top we have miles, and on the bottom we have the time, which is measured in hours. So we have miles per hour right there. So I would say that that represents the student's speed. And that it's 62 miles per hour. So when we are asked to interpret that constant, if we look at the units, that'll usually give us a pretty good idea of what's going on there. Alright, so we just finished up looking at direct variation, and now we're going to look at a new idea called inverse variation. So let's go ahead and look at the book's definition of that here. Inverse variation: if y equals k over x for some non-zero constant k, we say that y varies inversely as x, or that y is inversely proportional to x. And we call the variation constant, or the constant, we call k the variation constant, or the constant of proportionality. And the equation y equals k over x is called the inverse variation equation. And then the changes in values for the variables for inverse variation: assume that y varies inversely as x with some positive variation constant k. Then for positive values of x, if the value of x increases, the value of y decreases, and if the value of x decreases, the value of y increases. So when we have inverse variation, we always have the opposite direction of movement on our variables. If x goes up, y goes down. If x goes down, y goes up. So let's go ahead and look at an example of setting it up, and it's actually pretty similar to what we were doing with direct variation. So in our example, p varies inversely as d, and p equals 3 when d equals 5. Find an equation that meets these conditions. So when they say p varies inversely, we're going to write p equals, and instead of putting k times d like we would do if it said directly, we're going to put k over d when it says inversely. So that's the big difference. If it said direct, it would be k times. When it says inversely, it's k over. The rest of the process is very similar to what we were doing before. Once you get the equation set up, you want to figure out k. So you take the values of p and d that they gave and you substitute those in. So 3 for the p and the 5 for the d. Whoops. Supposed to substitute that 5 in there. And then we want to solve for k. So we'd want to clear fractions, so multiply both sides by 5. That would cancel the 5 over here. And then we get k equals 5 times 3, or k equals 15. So again, this isn't our equation. This was our equation, but we needed to figure out k, and we know that now. So we take the original equation, we take the k we just found, and we get our equation of inverse variation, which would be p equals 15 over d. So as you can see, that's very similar to the work we were doing before. It's just got that one change where you do k over instead of k times. And this equation with the k resolved and substituted in is the equation they were looking for. Okay, continuing on in section 12.8 with inverse variation, we're just going to look at a couple more examples here. If w varies inversely as u, and w equals 15 when u equals 2, then find w when u equals 6. So the key thing to notice is the varies inversely phrase. So that's going to mean that w is equal to k over u. Again, if it had said directly, it'd be k times, but with it inversely, we do over. And then we want to try and figure out k, and they gave us a couple values that'll help us do that. So we substitute in the 15 for the w, and the 2 for the u, and then we want to try and solve for k. We want to get rid of this 2. Currently that's dividing into k, so we do the opposite, which is multiplication. That cancels off the 2's, and we get k equals 30. And then, like we did in the previous ones, once you've figured out k, you use that to write your new equation. So w is equal to 30 over u. And then that was the end of our last problem because they just asked us to find the equation. This one goes on and says find W when U equals 6. So since they're giving us the value of U, go ahead and draw an arrow down there. We're just going to substitute that in. 30 over 6, and then 30 over 6 is 5. So W equals 5, and that would be our answer to that one. So again, very similar stuff to what we were doing with varies directly, just doing that initial change of division instead of multiplication with the k. Let's try one more. If d varies inversely as t plus 3 and capital D equals 5 when t equals 4, then find t when d equals 9. So again, there's that phrase, varies inversely. So d equals k over whatever they say next, and instead of just a variable they have an expression, but that's okay, we just still do the same idea. Instead of just the k over u like we had up here, now it's k over t plus 3, but it's still, because of the inversely, k over whatever comes next there. And then following our procedure, take these and substitute them in to try and solve for k. So d is 5 when t is 4, so we substitute that in. Maybe just one extra step here, because we need to go ahead and add the 4 and the 3 together to get to 7, but at that point we get rid of it just like we were before, multiplying both sides by that 7, we'll cancel it off, and at that point we get k equals 35. And we take that k equals 35 we just found, we put it into our original variation equation, and we get d equals 35 over t plus 3. And that's the equation, so I'd box that and stop if they had just asked me to find the equation, but they did go a little further and they asked me to find t when d equals 9. So I will substitute that 9 in for the d. And again, they're giving us the value on the left. These are always a little bit more complicated if they give you this value rather than that one. If they give you the one on the right, you'll just do arithmetic to simplify, but if they give you the one on the left, you're going to have to do some algebra. So I get this right here, and this one's a little bit messy. We've said before, and you've even seen us do it right up here, if there's fractions, you want to clear those. Well, that even applies if the denominator that you're trying to clear is an expression like t plus 3. So I would multiply both sides by t plus 3, so let me show you that on a new line. I'd say I have 9 times t plus 3 equals 35 over t plus 3 times t plus 3. So I'm just taking that equation that I had here and I'm multiplying both sides by the same thing. The reason I'm doing that is to get the fractions to go away by canceling that denominator. And then at this point I have an equation I need to solve. So I would distribute that 9, and that gives 9t plus 27. That would be equal to, all that's left on the right is 35 because the t plus 3's have canceled. Would subtract that 27 from both sides. I get 9t equals 8, and just enough room here to finish this off. We want t by itself, so we divide both sides by 9. The 9's cancel and we get t equals 8/9, and I'll just squeeze that in right here. So t is equal to 8/9. I'm putting a fraction here. If you're on my math lab, the default for you should be that you'd be putting a fraction, but pay attention to their directions. If they tell you to round it to 3 decimal places, then you just go to your calculator, do the 8 over 9, and you'd say t is approximately 0.889, rounding that in the third digit. So just pay attention to the directions. The default would be a fraction, but if the directions say to round it, then go ahead and do that. Alright, so we just did a couple models, and here's the generic template for the directions on that. Assume that p varies inversely as the quantity t, just like I added that step 0 before, I'll do that here too. That would mean that p is equal to k over t. And then you would substitute the values of a data point, which would be values of p and t that they give you, into the equation and solve for k. Then you put that value of k back into your original equation, and then you can use that to make estimates for t or p depending on which they give you and which they're asking for. Okay, all the examples we've done so far had just been kind of abstract, generic examples. This time we have a little bit of a setting on an application, so we can try and think about how this variation applies in context. So let's go ahead and read through the example. The intensity in watts per square meters, or W/m squared, the intensity I, which we'll use f of d, of a television signal varies inversely as the square of the distance d in kilometers from the transmitter. So got kind of chopped up there with the units, so if we read that kind of smoother, the intensity I varies inversely as the square of the distance d. So where's that phrase? Varies inversely means k over. So the intensity I is equal to k over, and then what did it say? The square of the distance. So the square of the distance would be d squared. And then it says the intensity is 30 when the distance is 2.6. So the intensity is I and the distance is 2.6, so that would be d. I can substitute those in and use them to solve for k. So the intensity is 30. That's equal to k over the square of the distance, which would be 2.6 squared. So we could clear fractions first, or we could substitute, or we could simplify this on the calculator. Either way should be fine. I think I'll go ahead and go to the calculator first. So 2.6 squared is 6.76. So we have 30 equals k over 6.76. And then, just like always ends up happening in these inverse variation problems, we want to cancel off that denominator, so I'd multiply both sides by 6.76. Did that on the right to clear fractions. I'll do it on the left just to keep things balanced. So k would be whatever this product is, so 30 times 6.76 looks like 202.8. So it looks like k is equal to 202.8. And that would give me my equation. I would have I equals k, which is 202.8 over d squared. And that would be okay for an equation, but it does say an equation of f. And they just said right here that f is the function name that we're going to use for the intensity, so I can just substitute that in, and instead of saying I equals, I can say f of d equals. So just take that last step, and we get f of d equals 202.8 over d squared. And that would be my equation of inverse variation, or my function of inverse variation actually, for this authentic situation. Alright, now that we have the function, they ask us to evaluate it and then explain what those things mean. So evaluating we can do quickly. F of 1 would be 202.8 over 1 squared, but 1 squared is just 1, and when your denominator is 1 you don't need it, so 202.8. And then f of 2 would be 202.8 over, and then we put the 3 squared, so that'd be 202.8 over 9. Whenever I have a decimal already, I assume it's okay to go to my calculator and give a decimal answer, so 202.8 divided by 9 is approximately 22.53. They didn't give any rounding rules on this problem. I'm sure they would in my math lab, so I'm just picking something reasonable and going a couple decimal places there. And I'm sorry, this is f of 3, and I worked it as f of 3, but I wrote a 2 right there, so let's just fix that up. So that should be f of 3. And then finally they want f of 5, so that would be 202.8 divided by 5 squared. So that 5 squared is 25. I'll do the division on that one. So 202.8 divided by 25 is 8.112. I know I only put 2 decimals on this one, but this is exact with 3, and rounding brings in error, so I'd rather give an exact answer if it's short than one that has rounding error in it. So there's evaluating all the functions, but I didn't do anything at all with the question of what do those mean. And I think the first step in figuring out what they mean is to think about the units. And so let's see, we were about figuring out values of f. F was the intensity, and the intensity is measured in watts per square meter. So I'm going to go ahead and put those units on. To be honest, I don't even have a great understanding of what that means because I don't have the strongest science background in the world. So I'm not putting units of watts per square meter because that just like totally makes natural, intuitive sense to me. I'm doing it because that's my output, and it said up here that the output was the intensity and that the units on that were watts per square meter. And then as far as interpreting that goes, let me just pick one and do that. I'll do the f of 3 right here. So what does f of 3 mean? Well, what was the 3? The 3 would have been the distance. And so the distance in this problem is measured in kilometers. So I would say for this one, at a distance of 3 kilometers from the transmitter, the signal intensity is 22.53 watts per square meter. And again, I think it's important to kind of relay the idea to you here that I am not an expert on radio transmission signal intensity. So when I write that, it doesn't even make a ton of sense to me, the 22.53 watts per square meter. That's not really intuitive to me what that means. But I'm just following the units of the problem and knowing that the input has the units of d for distance, and I looked at the problem to see that that was in kilometers. And then the output I know is intensity, and they said that that's watts per square meter. So I'm just following what they said for the units and saying at a distance of 3 kilometers from the transmitter, the intensity of that signal is going to be 22.53 watts per square meter.